and the first speaker is Liang, who's going to talk about complementary information and learning traps.
Great, so thank you so much to the organizers for organizing this and also for inviting me. So this is joint work with Xiaoxin Mu at Columbia. I apologize, by the way, I'm a little bit under the weather, so I'm anticipating a couple of sporadic coughing fits. Don't be too alarmed. So this project is about the dynamic production of information within a society and what causes a society to potentially get trapped in slower, less productive paths of learning as opposed to efficiently using its resources. In particular, we're going to be interested in the role of informational complementarities in shaping these long-run outcomes. Right, so what we do is we build a model in which agents are going to have access to multiple different kinds of information, and they're going to sequentially choose between them in order to learn an unknown parameter. So our main interpretation of the model is going to be research, actually. Okay, so we have a sequence of researchers, and there's some scientific parameter that the researchers would like to learn. Because of informational complementarities, there are going to be path dependencies, meaning that past research affects what is considered to be most valuable to learn today. If we had a central planner who was deciding what research everybody was going to be conducting, that central planner could then take into account these informational complementarities. We're going to be interested in contrasting the choices of a social planner with those that are made in a more decentralized information acquisition process, when the researchers themselves are actually working towards a more immediate goal, okay, like maximizing their immediate contribution to knowledge, as opposed to taking into account the effect of their own research acquisitions on the choices of future researchers. It's a short talk, so let me just jump straight into the model. We're going to have k different unknown states. One of these states is special in the sense that it's going to be payoff-relevant. That's this red omega. In addition, there are k-1 payoff-irrelevant unknowns, which are still going to be important because they're going to help correlate the different informational sources. We're going to assume that these unknowns are jointly normal. Agents are going to have access to n different sources or kinds of information, each identified with a coefficient vector. Okay, so the different signals are all going to be linear combinations of the unknown states plus a Gaussian noise term, okay, where the states are, again, persistent over time and the same across the different sources, but the coefficients are different across the different sources and also known to the agents. The Gaussian term itself we've assumed to be standard normal. That's without loss of generality because we haven't restricted the sizes of the coefficients. So in particular, say, if you were to scale up the coefficient on omega, holding all else constant, that's actually increasing the signal-to-noise ratio. Okay, we're going to assume that the noise term is IID both across time and also across the different sources. Just to give you a couple of different interpretations for what these confounding variables or payoff-irrelevant variables might model. So one instance is potentially we care about learning the level of dopamine in patients with a particular disorder. Right, so what you would really like to know is that level. How you might actually learn about that level is taking some sort of measurement of dopamine using potentially some sort of electroid sensor. That sensor, however, may be sensitive not just to the presence of dopamine, but also to the presence of various confounding chemicals. So if you don't know the levels of those confounding chemicals, that's going to affect the informativeness of the reading itself. Okay, so that's one possibility. Here's another interpretation closer to a regression framework. So maybe what we care about learning is something like the effect of micro-lending on poverty. Okay, that's this omega. And what you can observe is different cases of loan amounts as well as the corresponding reduction in poverty. Again, this reduction in poverty is going to depend not just, however, on the loan and its impact, but also on potentially many other covariates. The impact of these different covariates or controls you might not know ex ante as a researcher, and those are also going to affect, again, the informativeness of the actual signal that you observe. Right? So in each of these cases, you know the covariates, you just don't know potentially their impact, and the confounding variables in these cases would be the effects of the sort of less interesting covariates. So that's the informational environment. Let me tell you about the decision environment now. We have agents who are indexed by discrete time. They're going to move sequentially. Each agent does two things. So first, the agent is going to choose one of the n different sources of information, and he's going to observe an independent realization of the corresponding signal. Okay, so again, let me just stress that all of this is fixed, right? It's just every time you reobserve the signal, you get a new noise term. So first of all, it actually does make sense to repeatedly observe the same source, and what you just get is a more precise estimate of the error. Okay, good. So you're going to choose one of the sources, observe an independent realization of that signal, and then after that, you're going to choose a prediction for omega, and this is going to be the agent's payoff. What this means is that the agent is going to choose the source that minimizes his posterior variance about omega. And in fact, it's actually not so crucial that we even model the agent as making an action. So I think there are some cases in which having an action kind of makes sense. So maybe you make a recommendation or you take an action that depends on your evaluation of what omega is. But in some other contexts, we might think about the agents as directly just trying to improve knowledge or reduce uncertainty about omega within the society. So that would be an equivalent model. Throughout, we're going to assume that all signal realizations are public. So what that means is that agents are going to choose which source to observe, okay, and they're also going to choose what prediction to make based on the whole history of signal acquisitions thus far. Okay, in the research setting, we would think about that as meaning you get to observe all of the research studies that have been conducted and also their outcomes. And this is going to be an important departure from the social learning literature, which we're otherwise building upon. Okay, so in that literature, the standard model has agents observing actions that their predecessors take, but not observing the predecessor's private information. And the key learning friction is this sort of inference friction, where you're trying to back out information from the actions. If you actually just directly assume that people observe private information, then you actually shut down the interesting learning traps in that model. Okay, so what we're going to get, the learning frictions that we're going to produce are really going to come from this new channel of choosing between different kinds of complementary information. And then the main questions we're going to ask are, which information sources are going to be attended to by these agents in the long run, and also how does the speed at which the society ultimately ends up learning omega compare to what is feasible. So just to give you a quick preview of the main results, and what I'm going to show you is that informational environments fall into two different categories. So there's one category of informational environments where agents are actually guaranteed to achieve the efficient long-run speed of learning. Okay? This is despite the fact that they're acquiring information in this sort of decentralized or potentially myopic way. In another category of informational environments, there are going to exist potential learning traps in which agents get stuck acquiring information from these actually suboptimal sources that lead to inefficiently slow learning. Yeah?
Clarification, when you said learning omega, I thought omega was distributed. So is it estimating the distribution from which omega is sampled from?
Okay, good. So we should think about it as there is some true omega and true values of B1 through BK minus 1. They're just drawn at the start of time from this normal distribution. So you can also, you can think about the normal distribution as a common prior that all agents share about.
Now there's
but there is some truth.
Of the omegas and the C's or the B's?
The B's. Yeah. So these are the unknowns, the ones in color, and these are the knowns. Okay, good. So in this other category, depending on what the prior belief is, agents may in fact get stuck in these learning traps. And these environments are going to be differentiated by the structure of complementarities across the different informational sources. And I'll be much more explicit about exactly how. But before I do that, let me actually just give you an example of either case first. All right, so here's a simple environment, 3 different signals. The first signal is 5 times the state that you want to learn, omega, plus a confounding variable, B1, plus idiosyncratic noise. The second signal is a signal about the first confounding term. And the third signal is an unbiased signal about the payoff-relevant state. So I'll show you a result that will imply this, but for now, let me just tell you that efficiently what should happen is information acquisition should concentrate on the set x1, x2. And you can actually see that already, really, from the signal structure, because x1 minus x2 is itself an unbiased signal about omega. And that unbiased signal is more informative about omega than two realizations of x3. Remember, all of the noise terms are the same. They're all standard normals. Now, suppose, however, that agents have a prior belief where omega and B1 are independent, and moreover, agents have a lot of initial uncertainty about what B1 is. So now the first agent is looking at these three different possible signals. X1 is actually a really bad signal about omega because you have so much uncertainty about B1 that's really noising up the realization. X2 is not relevant, right? It's a signal about B1, and B1 is actually uncorrelated with omega, so you certainly wouldn't acquire X2. So the first agent is going to choose to acquire X3. Now, the second agent gets to observe the first agent's choice and also the realization, but that's not going to teach him anything about B1. So the second agent's thought process is actually identical to the first agent, and he too is going to acquire X3. Iterating forward, we actually have that every single agent in this environment is going to choose to acquire the signal X3. Okay, so intuitively what's going on is that it's actually socially beneficial for some agents to learn about this confounding variable B1, but no agent really wants to be the one who's actually going to go ahead and do that. Yeah.
But if I was looking forward, then if I think if I do X1 now, then maybe you'll do X2 next.
Right, yeah, so it's important here that agents' payoffs are really, yeah. So it's how much is my research studying improving.
All I'm ever going to know.
That's right, yeah. So in some sense, right, you can think about things like citation counts, or I'll talk about some other interventions actually near the end of the talk as being ways to potentially prevent agents from getting into traps like this. Yeah.
One research, one paper in their entire survey.
That's right, it's good. So one of the interventions we'll look at actually is allowing agents to, well, so the important thing is not whether you're allowed one or more, right? It's how your payoffs are evaluated. So are you getting paid for each paper one after one, or are you going to get rewarded on the basis of a body of work? And that's actually one of the interventions we'll be looking at. But even without going into interventions, it's going to turn out that in some environments, we actually don't need them, right? So in this one, we would. But consider this environment. Okay, so again, pretty simple. We have four different sources now. X1 is a biased signal about omega. X2 is a biased signal about the first bias term. X3 is a unbiased signal about the second bias term, B2. And then X4 finally is a signal that would be pretty informative about omega. Remember here that large coefficients are better. Right? It would be pretty informative, but unfortunately it's hit by both of these bias terms, B1 and B2. So in this setting, efficient learning should eventually concentrate on the set X2, X3, X4. And in contrast to the previous example, now it's going to be the case that starting from any prior belief, agents will actually eventually end up acquiring information exclusively from the set and actually in the right frequencies. So despite there are sort of myopic considerations or this decentralized information process, we actually have no long-run loss in welfare. So I'll say a lot more about what differentiates these two environments, but now just kind of at a high level, the key difference between the environments is that in this setting, in order to learn omega, agents inevitably have to also learn about B1 and B2. So there's no path for recovery of omega that doesn't go through these confounding variables. And what that implies is that an inefficient set such as x1, x2, x3, so you can see that that does reveal omega, okay, it does so sort of inefficiently slowly. That can't be self-reinforcing because once agents learn B1, B2 sufficiently well, which they will by repeatedly acquiring these signals, they would eventually then realize that x4 is actually quite valuable and switch out of that set. So here's the plan for the rest of the talk. I've been talking about efficient learning. Let me tell you more formally what the optimal sampling procedure actually looks like. And then we'll turn to our main question, which is how will agents actually acquire information? Will they achieve that? And then the last thing, two things I'd like to talk about, time permitting, are the extent of welfare losses under learning traps, so how bad are they actually, and then interventions, so what can a policymaker do potentially to get agents out of these traps. All right, so let's start with efficient learning. Okay, I'm going to need a definition before I get there, so this is a key definition in the paper. Actually, it's not the definition we use in the paper. It's an equivalent definition. I think it's a little bit easier to digest, so for the short talk, let me give it to you this way. All right, but the notion of a complementary set is key in the paper. So here, let me define a set of signals to be complementary if it is possible to learn omega from infinite observations of the sources in that set. And moreover, every source in that set is crucial for that recovery. So here's an example of a complementary set. Okay, so you should believe me that if I give you infinite observations of all of these sources, you will in fact learn omega. Additionally, you can note that if you were to throw out any one of these signals, that recovery would no longer be feasible, even with infinite observations of the remaining sources. Yeah?
So when you say every source in S is necessary for recovery, do you mean no subset learns?
That's right. So it's not possible to completely learn omega from any subset of the sources within S.
The following is fine. A subset plus another element that's not in S leads to...
That's right. That would be possible, right? But
This
this
is
definitely...
like linearly dependent subset.
Exactly. Yeah, great. Okay, so you've anticipated this claim. All right, so the characterization of complementary sets is that there exist unique non-zero coefficients, beta I, okay, one for each source in the set, such that it is possible to take a linear combination of the sources in the set. So here, Ci are the different coefficient vectors, okay, associated with the different signals. These are the weights we're going to apply to each signal. And we're going to recover the first coordinate vector, which essentially means the payoff-relevant state omega, just because, remember, that was listed first in the state vector. And also, there have to be unique coefficients with this property. So for example, if this is our set S, the coefficients are 1, 1 for the first signal, 0, 1 for the second signal. Indeed, it is possible to rewrite the first coordinate vector as C1 minus C2, and that is the unique decomposition in this way. The set is complementary. In contrast, if we look at this set, right here, these are the associated coefficient vectors, and now there's going to be many different ways to reproduce the first coordinate vector as a linear combination of these coefficient vectors. This is not a complementary set, and indeed, we don't want to think about these signals also as complementary. So actually, keep in mind these beta i's. That's going to continue forward in the talk. So one result is that optimal sampling from any complementary set leads to learning where long-run variance vanishes, like the expression there. Okay. And val S has the following expression. So we're going to think about val S as something like the informational value of the set. It captures how fast it's possible to learn given optimal sampling from that set of sources alone. Higher value means faster learning. And we make two assumptions throughout the paper. So the first assumption is that all complementary sets have distinct values that's going to be generically satisfied. A second assumption is that there exists at least one complementary set among the available signals. Together, these imply that there exists a unique best complementary set. So there's some set, and we're going to call this S star. So S star has the highest informational value, and equivalently, it also leads to fastest long-run learning among all of the complementary sets. Right, so that already immediately tells us that if the social planner were restricted to information acquisitions from some complementary set, what you would want to do is acquire information from S star. Okay, but in principle, the social planner has more flexibility than that. You can combine sets, randomize from sets. And what it turns out is that actually you can't improve beyond that. Right, so here, let's define lambda star to be the frequency vector that assigns 0 frequency to all signals outside of the best complementary set S star. And then within S star, samples each source in proportion to its beta I value. Okay, again, let me just remind you that the beta i's are the weights placed in this linear combination. So basically, the sources that are more important to that linear combination, which produces an unbiased signal, those sources should receive more weight in this frequency vector. So this turns out to be the optimal long-run frequency. And it's optimal in two different senses. So in the paper, we have one justification, which is purely a speed of learning justification. Okay, so this is the fastest way to recover omega. A different justification is payoff-based. So we consider a social planner that wants to maximize a discounted average of player payoffs. Okay, so again, remember, each player is predicting omega. And so we're going to fix some delta and look at the corresponding discounted average. And we can ask, what is the path of information acquisitions that would maximize U delta? For each such delta, there's going to be some strategy, which is the optimal strategy for that delta. And then we can look at every time step at the signal counts associated with that strategy. Okay, so d delta t tells us at every time t, how many times has the social planner sampled each of the n different sources. We can further normalize that to look at frequencies. So now lambda of t is going to be the frequency assigned to each source up to period t. And what this proposition says is that as long as delta is sufficiently large, sufficiently close to 1, it's going to be the case that the social planner's frequencies do eventually converge to this optimal frequency lambda star that I defined for you. So in both of these senses, lambda star is sort of what we would want the society to do, and based on these justifications, I'm from now on going to be referring to it as the optimal long-run frequency.
Yeah, can you say something about how large delta lower bar typically is? Say in
That's a good question. Yeah, I don't think we actually have a direct bound on this, but...
And what happens if this delta is lower than...
If the delta is lower, then it would be different, right? So if delta is sufficiently close to 0, then actually it's like the social planner would like for H's to act.
Can you say something about when it's lower?
Sorry?
Can you say something about when the discount factor is lower than this lower bar?
So when the discount factor is lower, then definitely this is no longer the optimal long-run frequency.
But do you know what is the optimal frequency then? How is that different?
Yeah, I don't remember. So that's something we can talk about offline. So it's definitely not this. And for example, if it's too close to 0, then you actually prefer the myopic path. But yeah, let's talk about that. Okay, good. So now we can ask, is it the case that society is actually going to end up acquiring information in this way? So first result, let me make a restriction on the signal structure. And don't worry too much about this restriction because it's only going to appear on this slide for this one result. So the restriction is that every k by k submatrix of the coefficient matrix C, which has the different coefficient vectors as its rows, has to have full rank. Under this assumption, it turns out that the potential learning traps are all complementary sets that have fewer than k signals, where again, recall that k is the number of unknown states. So formally, for every complementary set S, where the size of S is strictly smaller than the number of unknown states k, there's going to exist an open set of prior beliefs from which it turns out that S is exclusively observed. So you can see that in this learning traps example that I showed you earlier. So in this environment, k is equal to 2 because we have the two unknowns, omega and b1. X3 is a complementary set, right? It's possible to recover omega from this set alone. And that's the size of size 1, which is strictly smaller than k. So we didn't actually need the construction that I showed you previously. We directly know from this result that there must exist a set of prior beliefs that lead to exclusive acquisition of X3 in the long run. Right, here's another example. Right, so we might think of there as being different communities of signals, right? So maybe these signals are now people, they're experts. And the different communities of experts are all inflicted by a community-specific bias. So here, every pair of signals is itself a complementary set. K in this example is 4, so we have the 4 unknowns, omega, B1, B2, B3. And then again, applying the result, what we know is there must exist an open set of prior beliefs that leads to exclusive observation of any of these pairs of signals. Now, one of these cases is actually good, so this is the efficient set. And it's good that there are prior beliefs that lead to exclusively observing this. But these 2 pairs of signals we would then both consider to be learning traps. So what happens if there aren't any complementary sets that include fewer than, is that a question? Okay. So what happens if there aren't any complementary sets that include fewer than k signals? And in that case, it turns out that we get the opposite result. So from any prior belief, it turns out that actually efficient information aggregation is guaranteed. So there are no learning traps. Okay, so for any prior belief that we want to seed the community with, long-run frequencies are going to be given by this lambda star that I showed you previously. Okay, and correspondingly, agents are going to be exclusively sampling from this optimal set, S star. And so going back again to this example that we looked at previously, k in this example is equal to 3. We have omega b1 and b2 as the unknowns. And indeed, it's going to, it's the case, you can verify by inspection, that all complementary sets in this example are of size 3. So the condition
Quick
here
question.
is satisfied. Yeah.
What if you have like multiple sets of complementary sets of size exactly k?
Actually, I think that is this example, right? So there's multiple complementary sets, and they're all of size exactly 3.
Is there a distribution over all these sets, or just like one of them?
No, just one, and the best one. Yeah.
Sorry, what are the other complementary sets besides 2, 3, 4?
So there's x1, x2, x3, x1, x2, x4. Actually, every subset of size 3. Yeah. Right,
And
so yeah.
somehow in this example, even though x1, x2, x3 is complementary, we're still learning enough from those to know that eventually we want to add x4.
Exactly.
But
Yeah.
in the previous example where they were disjoint, they were also the same size.
For the previous example where there were disjoints,
Yeah,
which one? The learning trap example, or?
Yeah, the example with
Three different communities.
different communities.
This one.
It seems like they're also the same size here. I mean,
No, so k here is equal to 4, right? So it's not about comparing the sizes of the different complementary sets. It's about comparing the sizes of the complementary sets with k. Yeah. So here, okay, good. So thanks for these questions, because this will, allow me to make this a little bit more clear. So here, k is equal to 4, right? K is the number of unknown states. Okay, so omega b1, b2, b3, 4 unknown states. That's k. The different complementary sets, true, are all of the same size. What's important here is that that size is less than k. So that means that each of these are potential long-run outcomes. In this case, again, we have multiple complementary sets of the same size, but the difference is that now that size is identical to k. Right, so then we get a very different outcome where there's actually just a single possible long-run outcome, which is the efficient set. So even though they're all of the same size, that doesn't mean that they're all going to be attended to in the long run.
The coefficient is the beta.
That's right, yeah. So x2, x3, x4 is going to allow for the fastest speed of long-run learning. And that's where eventually agents are going to necessarily end up.
No matter where you start.
Sorry?
Where it doesn't matter where you start.
Exactly, that's right. That's right, so that's from any prior belief.
Oh, that's because the payoff is the minus of the variance of the estimation, right? The payoff of the agents.
So I hesitated, that's because, but, so what is the that in this? Yeah.
It's just the one that has the lowest variance of estimation is going to pick, which is the one that has the highest coefficient for double.
Right, but basically what we're contrasting is, so the social planner cares about the long-run variance reduction rate, right? But the agents are thinking about what is the variance reduction I'm going to achieve today. So it's variance reduction in both cases, but yeah. In some cases, the second concern already implies the first one, and in other cases it doesn't.
but just to make sure I understand, in that last example, if you were to add a new source,
Yeah.
x5, that was dependent on b3,
Okay.
a new variable, so k is then 4. But that shouldn't change this example being not having learning traps, right?
That violates something that we've assumed.
They have to remember what.
So you want to add x5 is equal to just b3.
Right, and then k is equal to 4, and then, but this set has the, did I misunderstand something?
Is this an if and is this a characterization or just one-sided?
So this is one side. I'll give you a characterization in a moment.
Okay, well,
So
let's see the
doesn't-
characterization then.
Yeah.
Yes, but
Yeah, so I mean, in that case, we should just drop b3 from the state vector.
Yeah, we don't need it, but,
yeah.
okay, let's see the characterization, or the other side.
Okay.
So quick intuition for this discussion we've been having. So the key force here is a learning spillover effect. So every time you observe a signal that looks like this one, so omega plus some confounding variable plus noise, you're going to learn both about omega, but you're also going to learn about this confounding variable. So what that means is that it's going to make future observations of that source more informative, and it's also going to make observation of any other source confounded by that confounding variable more informative. So now, suppose that agents are repeatedly observing some k signals that allows them to recover all k states. In that case, eventually you're going to be evaluating all of these sources under some sort of prior independent criterion, and this is roughly what's going to allow agents to discover the long-run optimal set. Okay. In contrast, if you're just observing some little k sources, okay, with little k strictly smaller than the total number of unknown states, then that's going to allow agents to maintain persistent uncertainty about the remaining capital K minus little k confounding variables. And what that also means is that some sources that are afflicted by those confounding variables may be persistently undervalued as well. Right, so in this case, you have to learn B1, B2. In this case, you might never learn about B1, and that's causing you to undervalue the signal first. All right, so now to the if and only if characterization. So I need another definition. We're going to say that a set S is strongly complementary if it is complementary, and also its informational value exceeds that achieved by any set, which is constructed by swapping out exactly one signal in the set S. Okay, so just one more time. We start with S. We're going to consider all possible sets we can get to by swapping exactly one signal. And what we need to be the case is that none of those swapped sets do as well as the original set S in terms of long-run speed of learning. Here's an example of a source that's complementary, of a set that's complementary but not strongly complementary. So let's start with x1, x2. It's a complementary set. But now suppose we swap out x2 with x3. So now we have x1, x3. That's actually going to be a better set in the sense that it allows for faster long-run speed of learning. So we're going to say that x1, x2 in this case is complementary, but it fails to be strongly complementary. And now for the if and only if characterization then. So agents are going to exclusively end up observing a set S from a set of prior beliefs, if and only if S is a strongly complementary set. So a couple of notes. So one note is that the best set S star, okay, the best complementary set, is itself always going to be strongly complementary. It's 5 minutes left. I see. Okay, so I should really rush from here. Okay, it's always going to be strongly complementary. Another observation is that if there is a unique strongly complementary set, then this implies that all priors go to the same thing. So in that case, we have efficient learning because, remember, S star is itself always a strongly complementary set. So that's got to be the unique strongly complementary set. Finally, if we have multiplicity, then different priors are going to lead to different long-run outcomes. And you can basically interpret the two previous results as giving sufficient conditions for either of these cases. All right, so with 5 minutes left, I'm going to be skipping a lot of this. Okay, so just have some examples. Let me basically tell you what's in the rest of the paper, and then if you're interested, you can take a look. All right. So we have a paper on the size of welfare losses under learning traps. So basically we say, look, so there's these learning traps, but really how bad are they? And what we do is we consider two different criteria. So one criteria is the speed of learning achieved by agents relative to the speed of learning that is actually feasible under the efficient information acquisition rule. And if we take that as our criterion, it's actually pretty easy to see that across different informational environments, learning traps can be arbitrarily bad. Okay, so we can do that by just taking this example we've been looking at, where we had a coefficient there, just replace that with an arbitrary zeta, increase zeta. Okay, as we increase zeta, we're going to make this learning trap x3 arbitrarily bad relative to the efficient set x1, x2. Okay, formally, this ratio of their informational values is unbounded as we increase zeta. Another criterion we might care about is long-run discounted payoffs. And towards this, what we do is we define the payoff that would be achieved if the social planner were the one choosing what information agents were acquiring. And we compare that with the payoff that is in fact achieved by the community.
So by the community, is the order exogenous, or everybody's identical exemptively?
Everybody's identical, yeah, right, so it's just where you are. Okay, good. So we can again compare these in a couple of different ways. If we look at the payoff ratio, similar arguments shows that that can be arbitrarily large. If we look at the payoff difference, however, turns out that that's actually always exactly equal to 0. The reason being that agents are always learning omega, even if they're doing so slowly in a learning trap. So that's really falling from our assumption that the states are perfectly persistent. And what we do next is we relax that assumption. We allow for slowly changing states over time. And we show that sort of arbitrarily close to perfect persistence, as long as there's a little bit of imperfection, then these learning traps do result in payoff losses and potentially large payoff losses. Okay, so I'll skip over this. But roughly, so we've presented an autocorrelated model in the natural way. We just take all of the different states and we index them to time. So the states are evolving over time, but agents are again going to be myopically acquiring information to learn about that period-specific state. And the main takeaway here is that one thing that we like is that the characterization of the long-run outcomes in the perfectly persistent state do actually hold as well, given a little bit of a change in the states. Okay, so, for example, the importance of strongly complementary sets, that remains. On the other hand, payoff losses exist as long as the persistence isn't exactly perfect. So specifically, this autocorrelation coefficient isn't exactly perfect. And then the last part of the paper looks at information and interventions for breaking learning traps. So let me just tell you about one then, going back to Ori's question. Okay, so one thing we might imagine doing is allowing agents to allocate multiple different observations across the different signals. Okay, specifically, we might imagine giving agents B observations. And you can choose where to put these B observations. So in practice, that might look like evaluating a body of work for the researchers, or it might look like more of a lab structure. You have a principal investigator, and they're choosing what everyone else studies. And here we have a positive result that says that as long as B is sufficiently large, then given acquisition of B signals every period, again, we can guarantee efficient information aggregation. Okay, one catch is that the number of signals B that's needed depends on the specific environment. So in particular, there's actually not a bound for B that works across all environments with the same number of unknowns K and the same number of sources N. So actually fine details of how the signals are defined matters for how many signal observations we need. How am I doing on time now? 1 or 2 minutes? Okay, let's do a few more interventions then. Why not? All right. In contrast, suppose we actually give agents B observations, but now we restrict it to be the same signal. Right, so instead of the previous interpretation, right, let's think about this instead as you have different people who are running lab experiments, and now we're giving them more funding. So you still run one experiment, right? You're choosing one of the signals to acquire. But it's just now that instead of having 100 subjects, let's say you have 1,000 subjects. So that signal is going to be more precise. In contrast here, we have a negative result. So all of the learning traps that existed for B is equal to 1, which is our main model, are still going to be potential learning traps for arbitrary choices of B. So it doesn't matter how precise you make the signals. And caveat, yeah.
Reducing the epsilon?
Exactly, yes. You can exactly thinking about this as reducing the variance on the epsilons. So a caveat here is that the sets of priors that make those learning traps are potentially different for the different choices of B. So if you fix a prior belief, and now you would change so we can think about it as change the epsilons, the variances on the noise term. It could be that indeed that intervention will break the learning trap. And in the paper, we have examples of both cases where it doesn't help and where it can. And again, that depends on fine details of the environment. All right, so let me actually just conclude now then with just a couple of more interpretations of the model or ways we can play with it. So here, I've assumed throughout a common prior belief. And we might alternatively think about a model in which there's actually multiple different communities, each seeded with its own prior. So for example, if there wasn't a global research community, we might think of there as being researchers in Israel versus the United States, and researchers within their country are passing down information over time, but they're not talking across one another. From this perspective, what our main result tells us is it the case that differences in prior beliefs will wash out eventually, so that eventually agents all end up within the different countries acquiring the same best informational sources? Or is it the case that differences in prior beliefs actually persist over time? And the answer was, if there's a unique strongly complementary set, then the priors are going to wash out. Everyone achieves the optimum in the end. Otherwise, if there's multiple complementary sets, strongly complementary sets, then we'll have persistent differences across the groups. Again, in our main model with persistent states, that doesn't imply different beliefs about omega in the long run, but if we sort of allow for the state vector to be changing over time, then we would also have persistent differences in the long run beliefs. Okay, and then a final comment is that here we've looked at choices between different informational sources. You can sort of think about a more general model that works in a similar way, where agents are sequentially choosing between different actions, and these actions have complementarities. So for example, managers at a firm might be choosing different actions over time. And you can ask similar questions about whether the agents will eventually achieve efficiency or not. The main issue is that you need some model of how those actions are actually related. In the informational setting, there's a very natural way of defining those complementarities via variance. All right, thank you.
Thanks a lot, Annie. There's time for maybe one more question, if there's any. We had many during the talk.
Yeah.
Okay.
So it does seem that the process of social evolution, this merge our scientific community to this solution, right? So people
Sorry, I
are
just didn't catch the beginning of that one more time.
through social evolution or whatever process, we did gravitate in the research community towards this solution.
Towards various solutions that are proposed here.
Towards the solution that you pointed out, that we are evaluated over a body of
Yeah.
research, and certain labs or researchers do try to capture the different sources.
Yeah. No, so I think that's right. I mean, I don't know if we've achieved the B that's high enough, but yes, so I think that's roughly right. And one intervention that I didn't talk about is actually funding knowledge exploration into learning about the confounding variables. And I think that also matches something that we actually do see, which is grant agencies that support methodological work or work that's not really interesting in of itself, but is actually an important complement to work that's socially interesting and important.
Right.
Didn't mean to say that methodological work is not interesting. It's not something you would tell a newspaper is on its own. Okay. Obviously, it's intellectually interesting. All right.
Thanks a lot.